Hello everyone and welcome to day 21 of the Jamb Physics in 40 Days series. I want to say a big thank you to each and every one of you that has been following the series from the very beginning. Thank you so much, and please keep your comments coming. If you have any question at all concerning what we're doing that you'd like to ask us, or if during your study you come across a question that is a bit difficult and you need help with, please put it in the comment section. We will definitely attend to all of your questions. And if you're new to this series, Jamb Physics in 40 Days is a series that is brought to you by Oyalen because we believe that when you dedicate within 30 to 45 minutes of your time daily, you should be able to get all the necessary skills and tools that will help you ace Jamb Physics. So if you're preparing for the Jamb exams and from your subject combinations, one of the subjects you have selected is physics, then these videos are made specifically for you. So please, you do not want to miss any video in this series. We've done day 1. This is day 21, as you can see. And each of the videos carry different topics that are in the Jamb Physics curriculum. We introduce you to the topic and what is expected of you, giving you tips as we go. And then we solve past questions on those individual topics. Like now, this is day 21, a different topic entirely. So you see why you do not want to miss any of the videos, because it's the combination of the entire videos in this series that makes your learning experience full and complete. So please check it out. And also don't forget to share these videos amongst your friends who are also preparing for the exam. Let's help everyone ace Jamb Physics. So please share, like the videos, and don't forget to subscribe to the channel, because when you subscribe, you're helping us to be able to make more helpful videos like this, and we really want to continue to do this for you. So please subscribe, and as you share, also ask your friends to also subscribe to the channel. Thank you very much as you do this. Now let's get to the business of day 21. So day 21 is about the propagation of sound waves, and what Jamb expects every candidate to be able to do as far as this topic is that every candidate should be able to determine the need for a material medium in the propagation of sound waves. You see, unlike the electromagnetic wave, sound wave is a mechanical wave, and the reason why they need material medium is that when the vibrations occur, they need those materials to transmit the vibration from one particle to the other and continuously like that until it gets to its destination. So when there are no particles to continue as transferring the energy in that wave, the wave will not be able to travel. So sound wave is that type of wave, a mechanical wave that need particles to continue to transmit the energy from point A to point B. So they really need a material medium. And this material medium can vary from solid, liquids to gases like the air, for example. So no matter which one it is, there just has to be a material medium. And which leads us to the second objective, which is that every candidate should be able to compare the speed of sound in solids, liquids, and air. And sincerely, there is a very simple thing, but many people just don't put it to mind. So let's look at it in this way. In solids, the particles that make up a solid, the molecules, they are fused together about a mean position. That is, they are so tightly packed, right? But in liquid, they are a bit free. And then when you get to gases, they are completely free. So you see the distance between those molecules are different. So for solid, the distance is very little because all the particles are packed together. That means that it is easier to transfer. It's just like this. If I'm here and then another person is right beside me, if I pick up something, I can immediately give it to that person. But if the person is away from me, I have to go a distance to be able to give it to such a person. That's in the case of liquid. But in the case of gases now, you have to travel a longer distance from one molecule to the other. So that tells you that the transfer of energy in solid is supposed to be faster, while in for liquids, it becomes slower, and then it is the slowest in gases. Take the speed of sound, since that's what we are focusing on here. Speed of sound in water is as fast as 1,500 meters per second. This is in water. Whereas in air, it is about 340 meters per second. Then when you get to solids, it is as fast as about 5,000 meters per second. So you see how the speed of sound varies in solid, liquids, and in air. So you should be able to understand this and also relate them one to the other. And then the third thing you're expected to do is to relate the effect of temperature and pressure to the speed of sound. Now, in the case of pressure, there isn't really any much difference like that. It's almost the same when you increase pressure or decrease pressure, because density and other parameters increase proportionally to pressure. So it doesn't really affect sound waves that much, but temperature has a big effect on it. And the relationship is that the speed of sound is proportional to the square root of the absolute temperature. So working with this, we can then say V1 over V2 equals square root of T1 over T2, like this. So this is the relationship. This should be V2. This is the relationship between speed of sound and temperature. And what it basically means is that the higher the temperature, the faster the speed of sound. So let's get that in mind. Now, moving on from there, you should also be expected to be able to solve problems involving echoes, reverberations, and speed of sound. Common formulas you're going to work with in that case is V equals F lambda. Other things you should know, especially in case of echoes, for example, is that the distance traveled will be the speed. Let's use V now. V multiplied by the time taken or divided by 2. Now the reason is this: for echo, it is actually a reflection. So the distance traveled is twice. So if this is the source of the sound, for example, and this is what reflects it back, it will travel this distance d when it's going, and then by the time it's reflected back, it will travel the same distance. So it will go twice this distance d, right? And since velocity is distance over time, so velocity is supposed to be twice distance over time, and we can always resolve it to be distance equals velocity times time divided by 2. So that's why the equation is this way. So you know you can always say V equals twice distance over time. So anyway, depending on what you're asked to find, whether you have to solve for time, solve for velocity, or solve for distance. Like in the case where you are trying to find the distance of a seabed, for example, once a sound wave is sent to the bottom of the sea and reflected back, you can always use this equation to get the distance. And then finally, I should be able to compare the disadvantages and advantages of echo. Now, where echo has some advantages, it really does have some disadvantages. Like one of the advantages is in the case of some animals like the bat that uses a technology called echolocation to move about. So you know that bats move at night because they are nocturnal, right? And they don't really have a good eyesight. So as a result, they emit sound waves and receive it back by echo to be able to tell if there's an obstacle in their path or not. So that kind of technology is called echolocation. And even to us humans, we use echo a lot. Like there's this technology in ships that is called the sonar. The sonar is just an you emit sound waves, and then if it meets any obstacle, it comes back and you are able to tell what kind of obstacle you met, right? And you can use this to detect when torpedoes are fired at ships. You can imagine how sound wave can help you detect torpedoes from enemy ships. So it has a huge advantage in that part. It's also used in mineral exploration, like in petroleum and other things like that, even in cave exploration and things like that. Echo has a lot of advantages. And in like way, it also has its own disadvantages. Like for instance, now we know that soldiers always have to break steps whenever they are marching. Because it has happened before that when soldiers were traveling and they weren't breaking steps, because of the multiple reverberations from their marching, a bridge collapsed which killed a lot of soldiers. So you see that when you don't put echo to good use, it can cause damages as well, because the reverberation has a lot of effect. So we always have to put it into consideration. And the same thing happens like those who do recordings like that. Like right now, we are recording in a studio, and you have to see that the entire walls of the studio is well padded to reduce echo, so that every sound that I emit right now will be absorbed by those parts that are in the walls of this studio. That way, you don't continue to hear my sound over and over. It can be as clear as possible. That is us putting echo to good use. If we had not factored that in during the development of this studio, you won't hear my sounds clearly. And it's not just for this studio, it goes for everywhere where there's recording. Even when you are recording on your phone, you always have to factor echo in. For example, you can try this, record a sound in an empty room and record the same sound in a place where there is a lot of things there. You discover that you hear yourself more clearly when there's a lot of things absorbing the sound waves than when you are in an empty room. The echo will distort the kind of sounds that you record when you are in that empty room. And that is one of the disadvantages of echo. So I believe we've been able to do justice to some of this that is expected of you. However, it's deeper than what we have just said. So if you want more from this, if you want to understand propagation of sound waves better, please check out our video where we explain this in detail. What we have just done now is a crash course, because we just want to look at what is expected of you and then move from there into solving past questions on the topics. Because we believe to take Jamb exam, you must have gone through each of these topics before, right? So we are just doing a crash course and then giving you tips when we solve problems. But to get a fuller understanding, check out our video on propagation of sound waves. We have done justice to that to explain every tiny detail that is expected that you'll learn as far as those topics go. So please check it out, and also don't forget to share, like, and subscribe when you check out those videos. And one more thing, you can also practice with the Exam Phone app. We're going to leave a link to download the app in the description box of this video. So please do well to click the link, download the app, and practice more. There's this common saying that says practice makes perfect, or so it is said. So please try out the app. I promise you will enjoy it because it is made in such a way that it makes your learning experience a fun-filled one. So please download the app today and practice with the Exam Phone app. So now that all has been said, let's look at some past questions on propagation of sound waves that has been said by Jamb in time past. And then I'll be giving you some tips as we solve those problems. So let's solve some problems. When we look at this question, we see that from a source of sound, it produces the sound wave in air, and we're given the wavelength as 1.65 meters and the speed of sound in air as 330 meters per second. So we are then asked to find the period of the vibrations. So let's solve that. Now, from the equation where we have V equals F lambda, this can be written as V equals lambda over T, where T is the period. Because relationship between frequency and period is that they are reciprocals of each other. That is F equals 1 over T. And that's what I have done in this place. So to find the period will therefore be wavelength over velocity of sound. So the wavelength is given as 1.65 meters, while the velocity is given as 330 meters per second. So all you need to do is just compute this, and it should give you 0.05 seconds. So our answer here is option B. This question involves echo, because you see that a boy standing some distance from the foot of a tall cliff claps his hands and then he hears the echo in 0.5 seconds later. So if the speed of sound in air at that location is 340 meters per second, we are to find the distance of the cliff from the boy, or the distance of the boy from the cliff. So let's solve. Now, we know that the speed is given, the time is given, we need distance. So the distance will be velocity times time divided by 2. And I gave this equation at the beginning of the video, so let's just apply it. So from here we can then say the distance is, velocity is 340 multiplied by 0.5 or divided by 2. Now this will give us 170 divided by 2. And then the distance is, now let's divide. This will go 8 times remainder 1 in 10, that's 5. So 85 meters. That is option D. This question also requires the application of the equation for echoes, but there's a slight difference now. Because in this case, we see a ship traveling towards a cliff, and then it receives the echo of its whistle after 3.5 seconds. And that's the first instance. You know, in this case, we can get the distance as, let's do that here, d1. That would be the speed of sound multiplied by the time over 2. So that will be v times t1 over 2, because the speed of sound is the same in this case. And then a short while later, it receives the echo after 2.5 seconds. Time change. So d2 will now be v multiplied by t2 over 2. So now we are asked to find how much closer the ship is to the cliff, given that the speed of sound under prevailing condition is 250 meters per second. So basically we are looking for the difference in the distance from d1 to d2. So we have to do d1 minus d2, which would be, now the v is what? 250 times t1. t1 is 3.5 all divided by 2. Then minus the second case, we have 250 multiplied by t2, which is 2.5 seconds, also divided by 2. Now, when you resolve what you have here, you will get this answer now, 437.5 minus, in the second case, we're going to get 312.5. And remember, this is divided by 2, divided by 2. And then when you resolve everything now, you should get 125 meters as the final answer. So from here, we then pick option D. This question is a bit similar to the other question we solved on echoes, but with just a slight difference. So let's examine it and see how we can solve it. So we are told that a ship traveling towards a cliff receives the echo of its whistle after 3.5 seconds. Now, a short while later, it receives the echo after 2.5 seconds. So if the speed of sound in air under prevailing condition is 250 meters per second, how much closer is the ship to the cliff? Now, in the first scenario, let's take the distance as d1. Now, d1 is going to be the velocity of sound in air under that prevailing condition multiplied by t1. Time t1 is the time it takes to receive the echo the first time, which is 3.5 seconds, all divided by 2. Now, in the second scenario, we'll name the distance there d2, and then that will be velocity multiplied by time t2. Time t2 in this case is the 2.5 seconds, all divided by 2. Now you note that the velocity is the same in both cases, so we do not change that. That's why we left it as v and v respectively. So what we are asked to find is the distance, as in the question itself says, how much closer is the ship to the cliff? So meaning we have to find the difference in the distance d1 and d2. So we'll do d1 minus d2. Now what is d1? d1 is v times t1. V is 250 times t1, which is 3.5 divided by 2, minus d2. We'll be having the same 250 now, which is speed of sound, multiplied by time t2, which is 2.5 seconds, all divided by 2. Now, when you compute this, you will get 437.5. So now we're going to do that minus, in the second case here, you will get 312.5. Now, the difference between this is 125, and distance is measured in meters, so that will be 125 meters. So our answer is option D. When a sound wave passes from air into water, it's and then when we look at the options here, we see that they talk about speed, frequency, and wavelength. So let's quickly look at what happens to speed, frequency, and wavelength when it changes from one media to another. So when a particular wave is moving, like sound wave in this case, moves from air into water. Now, as mentioned at the beginning of this video, I did say that the speed of sound changes depending on the media. And I mentioned that it is at the fastest when it is in solid to about 5,000 meters per second, and then in water is up to about 340 in water rather it's up to about 1,500 meters per second, and then in air it's about 340 meters per second. So you see that the media really affects the speed. So since in this case the sound is moving from air into water, we will see that the the velocity rather, is going to increase as it moves from air to water, and this is because of the closer proximity of the molecules in the media. So for air, the molecules are far apart, but in water the molecules are closer now, so that will make the speed to be faster. Now the same thing affects the wavelength. The wavelength is also going to increase. Now the reason why the wavelength is increasing is because of the frequency. Now you see, the frequency of a wave is determined by the source. Okay, like for example, the speed of light is determined by the source of that light, whether it is a infrared source, a visible light source, x-ray source. That is what determines the frequency of the wave. It's not the observer, it's not the medium, it is the source. So since the source did not change, the frequency will remain constant. And when we consider the equation V equals F lambda, if F has to remain the same while velocity is increasing, that means we have to increase wavelength. That's why I say that wavelength here increases together with the velocity while frequency remains constant. So please take note of this, because this question can be twisted in different manners. But in this case, our option is going to be the one that tells us that the speed increase, the wavelength increase while the frequency remains the same. So, and we see that in option A, speed and frequency increase, but wavelength remains the same, which is wrong. But B says speed and wavelength increase, but frequency remains the same. So this is the correct one. This one, yes, the speed does not decrease, and in this case we see that speed increase but frequency and wavelength remain the same. This is wrong. So we go with option B. Now in this question, we see a car moving at 20 meters per second, and the horn is blowing with a frequency of 1,200 hertz. Now, and it is chasing another car that is moving at 15 meters per second. And we are then asked to find the apparent frequency of the horn as heard by the driver being chased. Now, to solve a question like this, we use this equation using Doppler's effect. By applying Doppler's effect, we're going to be having the apparent frequency to be the frequency itself multiplied by the velocity of the sound in the source minus the velocity of the observer over velocity minus velocity of the source. And then we use this, and then we should be able to get our answer. So the apparent frequency therefore becomes, the frequency of the horn itself is 1,200. Now we multiply that by, now the velocity of sound in air is given as 340. So that will be 340 minus velocity of the observer, which is 15, divided by same 340 minus velocity of the source, which is 20, and then we close this bracket. So now what we have is 1,200 multiplied by, now the difference here, that would give us 340 25 divided by 320. So when you multiply this, you will get approximately 1.22 kilohertz. So that gives our answer to be option A. This question tells us that a plain sound wave of frequency 85.5 Hz and velocity of 342 meters per second is reflected from a vertical wall. Now, at what distance from the wall does the wave have antinode? Now, in this kind of case, the question can be twisted to at what distance from the wall does the wave have node? So take note of this. For the node, it will be lambda over 2 for node, while antinode is lambda over 4. For the first one, this is antinode. Now, the next one for this one will be at lambda, and then this one changes as well, and so on like that. But since it's the first one, for node is lambda over 2, for this antinode is lambda over 4, meaning we have to find lambda first, which is the wavelength. So here's the solution. So to find the wavelength is going to be the speed divided by frequency. Now the speed is given as 342 meters per second, and then we divide that by frequency, which is 85.5 hertz. And then when you divide, this will give you 4 meters as the wavelength. So now let's find the distance for the first antinode. So lambda over 4, and that will be what? 4 meters divided by 4, and that gives us 1 meter. So the correct answer is in option C. In this question, we are asked that if a sound wave goes from a cold air region to a hot air region, its wavelength will, that is what will happen to the wavelength of the sound wave. Now, we already learned that when a wave is traveling from one medium to the other, that the frequency remains the same, and this is because the frequency of a wave is determined by the source and not the medium, right? But we also know that the speed will change just as much as the wavelength will change. Now, what happens to the speed of sound when it moves from cold air to hot air? Now, as it travels from the cold air to the hot air, because the hot air has more energy. Remember that as you increase temperature, the molecules of a particular medium becomes more energetic, right? Because they vibrate more rapidly. This will make sound wave to travel faster in a hot air region than it would in a cold air region. And I did mention that the relationship between them is given as V is proportional to the square root of T. And then I went on to say V1 over V2 equals the square root of T1 over T2. So since we know that the relationship is direct, that means that as temperature is increasing, the velocity should also increase. Now, considering that V equals to F lambda, and F is supposed to remain constant. If F remains constant and we want V2 to be greater than this, it should then be F lambda 2. That is, lambda 2 should then be greater than lambda 1. So what will happen is that the wavelength would increase. So we go with option A. A cannon is fired from town X. After how long is the sound heard by town Y? 4.95 kilometers away. Given that the velocity of sound in air is 330 meters per second. Now, we know that this sound is going to travel this distance with this speed. So we just need to find the time taken. So this is how we'll solve. Since velocity equals distance over time, what this implies is that the time taken therefore will be distance divided by velocity. So the distance is 4.95 kilometer, which is 4,950 meters. Now we divide that by 330 meters per second, and this should give us 15 seconds as the answer. Therefore, we go with option D. Before I go on to solve this question, if you're yet to be subscribed to the channel, I want to use this moment to please implore you that you should please subscribe to the channel. We really need you to be subscribed to the channel so that we can continue to make more helpful videos like this. So please take a moment to just hit the subscribe button and also click on the notification bell icon so that you get notified every time I put out a new content. And also, because we want to reach a wider audience, we are pleading with you that you please share the videos amongst your friends. You just might be helping someone ace their next Jamb physics. So please share the video and also tell them to subscribe to the channel. We produce helpful content like this that help you improve on your academics. And so please tell them to subscribe so that they can continue to get all the help they need with their academics, and it is absolutely free. So one more thing also, if you have any question at all on what we are doing so far, or you come across a question while you are preparing or reading some materials and you would like help with it, please drop that question in the comment section and we'll definitely attend to all of your questions. Thank you very much for doing that. Now, in this question, we are told that the velocity of sound in air will be doubled if the absolute temperature is. So let's see what happens to the absolute temperature when the velocity of sound is doubled. Now, the relationship is that V1 over V2 equals square root of T1 over T2. Now, from what we have here, let's say V1 is V, and then V2 is twice of V. Okay? Now, T1, let that be T. So we need to find T2. T2 is what we need to find. So given all this, let's put it into the equation and see what we get. So V1 is V over V2, which is 2V, equals square root of T1, which is T, over T2. So from here now, we see that V cancels V. So we have 1 over 2 equals square root of T over T2. So to be able to get rid of this square root, we have to square both sides. So when you square both sides, you have 1 square, that's 1, over 2 square, which is 4, equals T over T2. Now cross multiply. T2 equals 4 times of T. Now if you recall, T is what? T1. That is T2 equals 4 times of T1. That is, it would be quadrupled. So our answer is option A. In a large telecommunication auditorium, perforated absorbent materials are used to line the ceiling so as to... Now, I did mention this earlier on in the video while I was talking about the advantages and disadvantages of echo. And I gave an example, like for example, in this studio where we are recording for Jamb Physics in 40 days, the walls, the ceiling, they are all padded with absorbent materials in order to do something, and that is to reduce echo and reverberations. Because if the echoes continue, the sound will not be clear to you that you are watching this video right now. So in order to avoid echo disturbing the sound, or distorting rather the sounds from this production, we have to limit echo. The same thing applies to large telecommunication auditoriums. They always line the ceilings, the walls with absorbent materials. So that is just to help them limit echoes and reverberations. So the answer to this question would be option D, which is reduce the reverberation of sound in the hall. The sound of an electricity bell dies down slowly when air is slowly pumped out from a bottle, because now in this case we know that a sound wave is a mechanical wave, and what makes it a mechanical wave is because it requires material medium for its propagation. So as the air is slowly pumped out from the bottle, the density of air in that bottle reduces gradually until the air is totally pumped out, and then it becomes a vacuum. And at that point, that is when the sound dies completely, because there is no air to continue the vibration, so it will not be propagated again from that point, since there is no material medium. That makes the answer for this C. Sound needs a material medium. Now, in this question, we are told that the sound from a source traveled to the bottom of the sea and the echo was heard 4 seconds later. Now, if the speed of sound in water is 1,500 meters per second, the depth of the sea is, so we have to find the depth of the sea, which is the distance. So, following the equation that we use when we are solving for echo, we know that the distance will then be the velocity multiplied by the time in which you heard the echo divided by 2. Now, distance therefore, which is the depth of the sea, would then be V, which is 1,500, multiplied by the time, which is 4 seconds, all divided by 2. Now, when you multiply this will give you 6,000 meters over 2. So the depth of the sea is therefore 3,000 meters. So the correct answer here is in option B. Now, this question mentions that which of the above will affect the velocity of sound in air. And then we have things like temperature, density of air molecule, pressure, and pitch. Now, we have already established that temperature affects the velocity of sound. So when it is in air, we know that the higher the temperature, the faster the velocity, right? And the same thing applies to the density of the air molecule. When you have a more dense air molecule, because of the higher number of molecules that you have in that case that are in closer proximity, it will make the sound to travel faster. However, pressure and pitch have no effect. In fact, pressure has little effect, but it's not really recognized as such. It's very little effect that is negligible. Pitch, on the other hand, does not even have any effect on the velocity of sound in air at all. So that makes the answer to be just 1 and 2 only. And that is what we have in option A. Now, in order to get in more practice, please download the Exam Phone app. We're going to drop the link to download in the description box of this video. So please click the link. That will take you to either Apple Store or the Google Play Store. And that depends on your device. So you get to the store and then download the app, register, and then have fun while you learn. Because the app is created in such a way that it makes your learning experience full of fun. It's just like a game setting where you have different levels to answer questions on the subject of your choice. And we have a lot of subjects there loaded with so many questions that will make your learning experience fun. And to make it even more fun, as you answer questions, you score points and also earn coin, which can be converted into money. So you can earn just as you learn. And also don't forget to subscribe to the channel if you have not done so already. Just take a second to click the subscribe button and the notification bell icon so that you get notified every time we put out a new content. And don't forget that we are here for you, please. If you have any question at all based on what we are doing, or perhaps during your study you come across a question that you need some help with, please put that question in the comment section and we'll definitely attend to every one of your comments. So as always, like, share, and subscribe. Thank you for following this series. I'll see you in the next one.